Automotive CAN and LIN Overview. We will review the applications, signaling, and protocol aspects of both the CAN and LIN interfaces. Here is a typical automotive body network example. The CAN bus allows for components to talk to each other seamlessly in the automobile. The LIN bus allows for further expansion to peripheral devices. This bus hierarchy was designed to save costs in wiring. Wire is one of the most expensive components in a car. It's heavy and often made by hand, which can cost lots of money. Anything that can be done to reduce wiring is done. CAN is the main bus in the automobile. It allows different modules to talk to each other, such as power seats, door modules, and climate control units. It's a differential two-wire interface operating up to 1 megabit per second. Future CAN FD implementations will allow speeds faster than that. LIN is a sub-bus. It allows modules to talk to sub-modules such as heater, motor, locks, mirrors. Automotive CAN interfaces are dictated by the ISO 11898 standard. There are 6 parts to the standard. Part 1 is the data link layer and physical signaling. Part 2 allows for high-speed medium access. Part 3 allows for low-speed fault-tolerant medium-dependent interfaces. Part 4 is time-triggered communication. Part 5 is high-speed medium access unit with low power mode. This includes all the requirements of Part 2, yet adds low power mode requirements. Part 6 is high-speed medium access unit with selective wake. This is sometimes referred to as partial networking. The ISO 11898 standards and car makers' naming conventions have generated a lot of confusion by using terms like low speed, medium speed, and high speed. The ISO 11898 CAN standards and transceivers implementations fall into 2 categories. High-speed CAN, governed by parts 2, 5, and 6 of the standard, operate from 0 bits per second up to 1 megabit per second. TI Turbo CAN transceivers for industrial applications can go faster than the 1 megabit per second ISO specification. Low-speed fault-tolerant CAN, governed by Part 3, operates from approximately 15 kilobits per second up to 125 kilobits per second. It should be noted that there's an overlap in operating speed from approximately 10 kilobits per second to 125 kilobits per second between the high-speed and low-speed fault-tolerant CAN. Some car makers use only high-speed CAN physical layers, governed by parts 2, 5, and 6, but use the following names to describe the operating data rates of their networks. Low speed, which is 125 kilobits per second, medium speed at 250 kilobits per second, and high speed for 500 kilobits per second. There are many additional CAN-based standards and protocols. Higher layer protocols govern aeronautical, agricultural, embedded, industrial automation, military, marine, and safety critical applications. Each of these higher layer protocols also have additional test standards that govern EMC and ESD. The CAN physical layer has 2 wires, CAN-H and CAN-L. The difference in the voltage between CAN-H and CAN-L is called VD. A logic 1 is represented by the recessive state and is defined as VD less than or equal to 0.5 volts. A logic 0 is defined by the dominant state when VD is greater than or equal to 0.9 volts. A CAN-compliant driver must produce at least 1.5 volts across a typical 60 ohm load. CAN is designed to be used with twisted pair cabling with 120 ohm characteristic impedance. The network should be wired in a topology that limits stubs as much as possible. The bus should be properly terminated at both ends with resistors that match the impedance of the network. This helps to reduce signal integrity issues like reflections. If nodes may be removed from the bus, care must be used on where to place the termination resistors. Termination may be a single 120 ohm resistor at each end of the bus, or a split termination may be used. Utilizing split termination improves signal integrity and electromagnetic emissions. Split termination eliminates fluctuations in the bus common mode voltage levels. Since CAN networks may be shorted to voltage sources, the power ratings of the termination resistors should take into account the short circuit current protection of the CAN transceivers in the network. The CAN data frame begins with the start of frame. It's a dominant bit that begins the frame and initiates arbitration. This is followed by the message identifier, which is an 11 or 29-bit identifier used for arbitration priority. The control field specifies the length of the data to be transmitted. This is followed by the data field and the CRC. The ACK field is used to acknowledge the CRC status of receiving nodes. The end of frame marks the end of the data frame and remote frames. The CAN physical layer allows for priority-based arbitration, which is based on the 11-bit identifier of each module. All zeros is the highest priority identifier, and all ones is the lowest priority identifier. During each bit of the identifier frame, each node will monitor the bus and compare the bus state with the state it is driving. If the transceiver transmits a logic 1 and receives a logic 0, it will stop transmitting. The node will attempt to access the bus again after the next interframe spacing occurrence. Loop time in CAN. The maximum length and operating rate of a CAN bus depend on several factors. The CAN controller I/O, the TXD and RXD, is negligible. CAN transceiver driver and receiver delay, often called T-loop. Cable length, max cable length of 40 meter at 1 megabit per second, given a 5 nanosecond per meter typical delay value. Other delays introduced by additional series component, such as isolators. Arbitration is the key to a CAN network. Knowing the loop and round-trip delay is critical. Each node must know the total round-trip delay to ensure it waits long enough before sampling the bus data, or the faster node may sample the bus data before the slower node bit state transmission. Each component in the system contributes to the total round-trip delay. For instance, the round-trip delay is 2 times the T propagation from node A to B, the isolator delay, the transceiver delay, and the controller I/O delay. Each node needs to know its own TXD to RXD loop delay as well as the round-trip delay, so that it is programmed with an appropriate sample point to accommodate worst-case delays in the network. Faster loop times allow for more propagation delay budget for isolation devices and/or longer cables without compromising data rate. Specific parameters related to timing and synchronization can be set up in the CAN controller to accommodate propagation delays. In a CAN frame, a bit of opposite polarity is inserted after 5 consecutive bits of the same polarity. This practice is called bit stuffing and is due to the non-return to zero coding adopted by the standard. The stuffed data frames are destuffed by the receiver. Since bit stuffing is used, 6 consecutive bits of the same type are considered an error. Another important aspect of the CAN protocol is the acknowledgement. The ACK bit occurs after the data and CRC fields and allows a receiver to indicate back to the transmitter that the frame has been received. During this bit, multiple CAN transceivers may be driving dominant simultaneously. Here is the 8-pin CAN standard pinout. The TXD, RXD, CAN-H, and CAN-L are present on all 8-pin CAN transceivers. Additionally, some transceivers implement either standby mode or silent mode. In standby mode, the driver is disabled while the receiver is in a low power wake-up mode. For silent mode, the receiver is enabled and mirrors the bus while the driver is disabled. The VIO or split pins are also available on some transceivers. The VIO pin provides a separate supply voltage for the transceiver I/O pins TXD and RXD. The split pin provides a VCC over 2 output to stabilize the bus common mode voltage for applications using split termination. Here is a CAN node configuration example for a car. Each node has a processor with a CAN controller and transceiver. There are optional external components that some systems may have. Diodes for ESD or transient protection on the CAN bus lines outside of the CAN transceiver spec. Split node termination with common mode bus stabilization output. And some MCUs do not have internal pull-up resistors and will need an external pull-up for fast data rates. CAN with flexible data rate is typically referred to as CAN-FD. It's an enhancement to the CAN protocol which increases usable bandwidth up to and above 2 megabits per second. Two key differences between CAN and CAN-FD protocols are the data rate and the data field length. CAN-FD frames have the option to have separate data rates for the arbitration and data portion. Arbitration portions adhere to CAN, while the data may be transferred at a higher data rate. CAN-FD frames allow for data fields up to 64 bytes, 8 times more than standard CAN. Increased bandwidth is one of the major advantages of CAN-FD. The 8-byte limitation of the CAN data rate is constraining for some applications and requires multiple messages to send the requisite data. With CAN-FD, you can send the same data in half the time as standard CAN, or 2 times the data in the same amount of time. It also has lower relative cost and complexity. With a small incremental cost to increase bandwidth and less complexity than implementing major network changes such as FlexRay or Ethernet. Fast flash programming. CAN-FD also allows for fast end-of-the-line flash programming of modules and ECUs, reducing manufacturing costs. What system components are impacted by CAN-FD? The CAN controller and the microcontroller is one. Hardware changes may be limited to the CAN controller and the microcontroller, assuming a data rate above 1 megabit per second is never used. The CAN controller and the microcontroller or protocol engine must be updated to the new CAN-FD standard. CAN-FD will be backward compatible to classic CAN, however original CAN controllers are not forward compatible to CAN-FD. Physical layer, the PHY or transceiver. Original CAN transceivers, cabling, connectors, protection circuitry meeting the CAN requirements for 1 megabit per second may all be used for CAN-FD at up to 1 megabit per second. Just like CAN, CAN-FD will scale down in data rates based on long cabling and high node count or loading. Greater than 1 megabit per second CAN-FD data rates may require changes. Software. Low-level drivers for the new CAN controllers on the MCU must be updated to new register map and longer payload options. Application software must be adapted to handle the longer data payloads. 14-pin CAN transceivers keep the same base functionality as 8-pin transceivers, but add several different functions, such as the ability to run off a battery in low power mode, advanced fault detection, and the ability to signal the rest of the system to start up based on wake-up commands issued via the wake pin or CAN bus. The Local Interconnect Network, or LIN, is a broadcasting serial one-wire interface typically implemented as a sub-bus of a CAN network. It allows automotive manufacturers to reduce cost by offloading low-speed, non-safety critical functions from a two-wire CAN bus to a one-wire bus. One master coordinates communication between up to 16 slaves. The LIN physical layer is considered recessive when the voltage on the LIN wire is less than or equal to 0.4 times the supply voltage. It's considered dominant when the VLIN is greater than or equal to 0.6 times the supply voltage. The LIN protocol specification defines all types of frames that may be sent on the LIN bus, the fields that make up each type of LIN frame, and the order of the bits in each field. The physical layer specification is unchanged for specification versions 1.3 through 2.2a. Thank you for watching.